integrating OBO ontologies into a unified semantic graph. Go ahead, Jim.
Great, thank you, Alex. Thanks to all the organizers of the conference. It's been a great few days. Yep, so I'm going to talk about this service called Ubergraph that I've been working on, and I want to acknowledge my co-authors, Uger Bayandir, Anita Karen, David Simi-Sutherland from EBI, Nico Matansoglu of Semantically, and Chris Mungle from LBNL. And so what is Ubergraph? There's going to be kind of two angles that I'll be talking about. And, it's sort of both a particular online resource that you can use. It's an RDF knowledge graph of OBO ontologies, and right now there's 39 of them in there. And it's basically a public SPARQL query endpoint. But also it kind of takes a particular approach to rendering out ontologies as knowledge graphs, and so that to me kind of provides a really ergonomic way to traverse relations between terms and do queries, and it also gives you access to sort of full class and relation semantics, at least for something like OWL. And so, why am I calling this an OBO knowledge graph and not an ontology repository? So we have a number of ontology repositories already, so this isn't trying to do that. We have things like OntOB and OLS, BioPortal. So, but if you look at the OBO mission on the website, it says, and I think everybody knows OBO is the Biomedical Ontologies Foundry. It's to develop a family of interoperable ontologies that are both logically well-formed and scientifically accurate. And so interoperable is kind of the key word here that I'm thinking of. And so we have different ontologies, like about anatomy or chemistry or biological processes. So these are developed kind of independently and on their own schedules. There are different communities of editors, but they're to a great extent very mutually referential. And so like all of these particular ontologies all depend on each other and have axioms that reference terms from the other ontologies. And so just to kind of go into one example of like how this works in real ontology. So in gene ontology, you have a structure like this. These are some different biological processes related to metabolism. And so you have something like glucose synthesis is a type of glucose metabolism. And is also a type of carbohydrate synthesis. And so you can imagine that you have this lattice here, and with more chemicals and more kinds of processes, it's quite complicated to maintain the proper sort of subclass relationships. And so luckily, we don't maintain them like that. They get inferred. And so in practice, you have, the gene ontology is sort of focused on this hierarchy of metabolic processes. And then Kebi, is who tells us that glucose is a subtype of carbohydrate. And so they can kind of work on those core hierarchies in those separate projects. But so then in Go, these terms, for carbohydrate metabolism or glucose metabolism are defined using OWL expressions. And so you have this logical definition, like where carbohydrate metabolism is the intersection of everything that's a metabolic process and also things that have input or output some carbohydrate. And so by writing these logical definitions like this, then we run this through an OWL reasoner, and it computes that what are the exact subsumption relationships like between all of these classes. And so this can be made even more simple using like something like DOSDP tools, where you can kind of standardize all of these definitions and just sort of have a TSV of, all of the all of these catabolic processes for this list of chemicals. And so, there are some more complicated examples. So this is a term from human phenotype ontology, astrocytosis. It referenced to 5 different OBO ontologies in this axiom. And so what this term means in HPO is dependent on all of these other ontologies as well, and they kind of all need to be taken together to compute a classification for astrocytosis. And so this is just a representation of most of the ontologies that are in Ubergraph now. and how they're interconnected. So the ones on the left are referencing terms from the ontologies on the right. And so the thickness of the line is just how many terms are used within axioms. And you can see, the thicker ones, so Go and MP at the top there, they both use a lot of external terms. And then, for example, on the right, I think the biggest two are Uberon and Kebi that are both referenced within other ontologies quite a bit. But even there's many, many thin lines here as well. And so there's only a few ontologies that I have in Ubergraph right now that don't really reference other OBO ontologies. And so I think this kind of indicates that having a merged ontology, union ontology or ontology knowledge graph is a useful thing. And so something that's really convenient is that these ontologies being available in OWL that can be natively saved as RDF, and you can just stick them into an RDF triple store database with kind of zero effort. But there's some challenges in really doing anything with that. So there's kind of two aspects of it. One is just sort of a syntactic. What you're really putting in there is kind of ontology source code, like that the way OWL looks in RDF is a representation of the axioms, but it's not necessarily the best view of an ontology as a graph. And Rob kind of talked yesterday about the idea about ontologies being graphs or sets of axioms. But so Ubergraph is kind of looking at how to represent ontologies as graphs if you want to work with it as a graph. So there's also semantic issues that a lot of the graph connections that are logically implied aren't stated because you're supposed to be using an OWL reasoner and have that OWL semantics available to you. And so just to kind of dig into like what these problems look like, there's a lot of people might be familiar with OBO file syntax. And so on the top left, you have this term glucose synthesis that has the name gluconeogenesis. And you can see it is a biosynthetic process, and it has a relationship to has output of glucose. And so a lot of folks look at this, think of this in this kind of directed graph view down in the bottom left. Rob also yesterday mentioned DAG edit, which I was also thinking about mentioning how that was kind of how a lot of the ontology editing started, was sort of working just with directed graphs. And so SPARQL is a really great language for querying over graphs. And you might think, if you want to say, we have this merged ontology store, what processes output glucose? And so maybe you would want to write it like this. There's some variable of a process and has output relation to glucose, just the Kebi ID. So that might be kind of the way it would be nice to write it. But in practice, it's not how it looks when you put OWL in RDF. And so a lot of people who have worked with the RDF level OWL are probably very familiar with this. The relationship of the has output, it's an OWL existential restriction. And so it kind of is made up of these four triples that its on property has output and some values from the Kebi term. And so that's not very pleasing, like to query and to have to write all that stuff down when you're trying to write a SPARQL query. So and it's even worse than that, really, because the Go term gluconeogenesis is something more like this, as an equivalence axiom to that expression of process that outputs glucose. And so in the OBO syntax, it uses these intersection of lines. And then so if you really wanted to write a SPARQL query over that, you'd have to write this intersection of property and then kind of dig into this list of the operands of the intersection. And so that's just kind of becoming unusable. And so that's sort of just a structural thing, but then, what about the semantics? And so if you want to know, which processes input or output a carbohydrate, you would like to know processes that work with any carbohydrate, any, like glucose. And the relation ontology has this super property called has participant, which is entailed whenever for has input or has output. So we could put that into our query, and so we could maybe use the SPARQL property path and get all the sub properties of has participant and all the subclasses of Kebi. But we've kind of handled some of the semantics, but there are property chains in relation ontology, and then some of those terms in the property chains are transitive properties, and so we kind of have to go across the whole chain. So it's kind of impossible to do this without a reasoner, and so if we put all these ontologies into a reasoner, we could just submit the DL query like down at the bottom, has participants some carbohydrate, and then you should get all of the processes that are subsumed by that. But so should we just load all of the ontologies into Protege at once? You know, for the big set in Ubergraph that all kind of connect with each other, it takes maybe 30 minutes or so to load them all up into memory and then run the ELK reasoner, and Protege gets really slow. So it's not really a viable way to do that. Some triple stores that are available incorporate reasoners. Usually they're kind of focused on instance classification and not so much doing like terminology queries that we're talking about here. And so the solution that Ubergraph takes is this precomputed relation graph. And the idea with that is that we just materialize every implied edge between every named class as simple RDF triples. So if there's an inference that A is a subclass of B, well, then there's a triple in there that says, you know, A RDFS subclass of B. And if it's inferred that A is a subclass of this existential restriction, like R sub B, so that's how all those relationships are represented in OWL, then it, for everything of that form, it puts in a simple triple A, R, B. And so it does that for every possible inference. And so there's no reasoning that has to be done at query time. And so just for something like gluconeogenesis, all of these triples are in the database, like that it's a subclass of biosynthetic process, but then also a subclass of all of the processes, you know, that are superclasses of that, metabolic process, biological process. There's a triple that says it has output glucose, and then also, you know, every chemical above that up to chemical entity, and then all of the super properties. So it's just an exhaustive materialization. And so this is done with this tool called Relation Graph, which is something that I have written. It's based on the reasoner that I spoke about in the tools workshop the other day. It works well with that reasoner because it can do these DL queries very fast and in parallel. And so it just computes for every property and class in the ontology. It takes the cross product and executes basically every query R sum C against the ontology. And, you know, for every subclass of that expression, it outputs a triple like this, XRC. And so it does this in parallel, but it also avoids unnecessary queries just by kind of being smart about how it's traversing down the hierarchy. So, but kind of the theoretical number of queries, like for Ubergraph, is something over, it's almost 4 billion, I think, but it can do it fairly quickly. And so it streams the output into an in triples file, and so you can use this offline against just one ontology, or, you know, I use it in the Ubergraph build. It's also being integrated into Robot. And so it's just some examples of the kind of queries then you're able to do. It looks pretty much like that sort of idealized query that I started with. So I want to know which processes output glucose. I can just write this SPARQL query here. You know, a variable process has output, you know, the Kepi ID for glucose, and I can also get its label. And, you know, you get these two terms back, which are all the processes outputting glucose that are in the data set. You can kind of go the other direction, which is something that you can't really do in Protege with the DL query interface. You can say, you know, what things do we know that adrenal gland is part of? And so you get abdomen, chromaffin system, but then you also get, you know, these much higher level terms. It's part of an anatomical entity, it's part of an independent continuant. So you kind of see it's sort of logically complete, but you know, so you just get both very specific things and also all these very general terms back. So there's, I guess, about 38 results for that query. And so you can make it a little more complicated. And so we can just say, you know, which things are subclasses of cell and are part of something that's a subclass of organ, and where that organ is part of the abdomen, and get to the labels also. So things like mesonephric podocyte is in the mesonephros, splenic fibroblast is in the spleen. And so, yeah, it works quite well and quickly. So all these queries, if you look at the slides later, there's a little link that will run it for you. on the GUI SPARQL query editor. So you can do other things just like checking entailments, like which is also kind of not too easy to do directly with OWL. So, you know, for Uberon, we want to make sure that there aren't any things that are bone elements but haven't been inferred to be part of the skeletal system. And so we just get all the subclasses of bone element and get all the ones that don't have a triple connecting them to the skeletal system. And there's no answers, so that's good. So there's another kind of relation graph that's available in Ubergraph called the non-redundant graph. And so that lets you traverse this knowledge graph more incrementally. And so it contains only what I call direct edges. And the definition of what is a direct edge isn't really universal. So I have a sort of set of rules that I'm using, but there's some other possibilities that you can come up with. But you know, for one thing, it takes all of those redundant, logically complete edges, and it removes any of them that you could recapitulate by using like a property path in SPARQL. So anything that's a transitive property, it only has the most specific relation. It also takes out any edges where they have the same subject or predicate as another edge that has a more specific object. That one's considered redundant. And if it has the same predicate and object and a more general subject, then that's redundant. So, and then so on, like same subject and object with a more specific predicate. So these are all the kind of rules about this filtering. And so this sort of filter down graph is really useful for creating like an ontology browsing UI or term info or something. You can kind of see this sort of most direct relations to a concept. And so this pruning happens in the Ubergraph build using this souffle data log script that implements these rules. So this is sort of what the non-redundant graph looks like if you do a query for all the terms that are like one hop away from Uberon I. You get, you know, it's a subclass of sense organ, it's part of the visual system, capable of detection of visible light. But it's a bit more than you get just by looking at what the ontology says. So there are inferred relations here, but it's only kept the ones that are sort of not redundant with some other class. And so for all these same classes in this picture, so this is just to kind of show the difference. You can't really look at all this stuff, but these are all the edges that are in the full logically complete graph, like between those same concepts. If you had done a query of what are all the terms that are one hop from I in the redundant graph, it's something like 1,000 or 1,500 terms due to just all the inferences that are stored. And so just some specifics about Ubergraph now. Yeah, I already said there's 39 ontologies there, and it's been kind of growing outward from Uberon, which is where it started. So it kind of started when someone at Rinci asked me how they could query for which cell types were connected to which anatomical structures in Uberon. So it sort of started working on that then. It already has KEBI and NCBI taxon and prose, which are some of the biggest ones. So if you need to do some queries over the graph structure of those ontologies, you don't need to download them all. You can just submit it to Ubergraph. So there's a little over 500 million triples, and which like the majority of which are in that full relation graph. And it takes about 4 hours to build that graph, another hour to run the pruning algorithm. And you see the makefile that builds everything on GitHub. And this is deployed at Rinci using BlazeGraph as the triple store. And so if you want to access it, there's a public SPARQL endpoint. So, you know, don't go to that URL. That's just a SPARQL service endpoint. So you could run that, run queries against it using something like YassGUI, which is this tripledb.com website. There's also the ontology access kit, which Chris Mungle has been building. And he has some built-in connections to Ubergraph in there. So you could, for example, do this command run oak, tell it -I Ubergraph, and you could visualize, you know, 2 relations away from Go photoreceptor outer segment. You can just generate pictures like this with very little code. You can download everything. There's an nquads file, which is the full database. You can download through a link that's on the GitHub repo. There's also some simplified node and edge tables just for the redundant and non-redundant graphs that are kind of suitable for looking into some machine learning tools. And so who's using it? Well, biomedical data translator program that Susan Kuguric had mentioned. It's something that folks at RINSI are involved in, and they're developing this federated knowledge system integrating existing biomedical data sets. And a lot of those data sources in translator reference OBO ontology terms. And so Ubergraph provides, links between those terms, kind of gives the contextual knowledge of which ones are subclasses of each other, or which cell types are related to which organs, things like that. We have a web service that kind of wraps Ubergraph and submits queries to it, but then provides the data in the data translator API. Ubergraph has a graph of links to BioLink model categories as part of it, which is kind of relevant to data translator. That's sort of the data model that unites it. The Mondo disease ontology development team uses Ubergraph quite a bit just for ad hoc queries, doing like initial versions of QC reports and exploring inferred connections. Mondo is like really large ontology. It takes quite a while to download it and load it into Protege. And so it can be easier to sort of start off just submitting some SPARQL queries to Ubergraph. And then after kind of prototyping those are often then baked into the build pipeline for Mondo as QC. There's a project called HubMap, which David Assimi-Sutherland at UVI is involved in. And they're building this human reference atlas with expert input. And so they've built this Python workflow that is based on Ubergraph, where the experts provide these spreadsheets describing expected connections between terms that are part of their atlas. And so the workflow validates these against Ubergraph. And so, does this relationship exist, or is it asserted or inferred? And or if it doesn't exist, what for what term they're asking about, what is it part of, or what does it overlap? And so they have this kind of feedback loop workflow that they've implemented. And I think Ubergraph made that much quicker to implement than it would have been otherwise. So some of the challenges that we have run into, so going back to something Rob mentioned yesterday in his talk, logical incompatibilities that you run into when you merge OBO ontologies together. And so I really think that this problem is largely solved. We've done a lot of work on just reasoning tools and QC workflows and everything with the ODK in the last couple of years that has really changed just a lot of the production process of OBO ontologies. And so there are many fewer issues with kind of missing axioms and connections up to BFO constraints and things like that. So we find those issues earlier now. And a lot of the problems really were version mismatch, where one ontology, for like Go would have a piece of Ubron that it had imported maybe a few months earlier. And then if you combine that with the latest Ubron release, there are just different versions of Ubron, and there's some change that's incompatible. But it's kind of happenstance with sort of which pieces and what time these import files were made. And so a lot of OBO ontologies make available these things we call base releases now, which are just the axioms of that project and don't include imported axioms. So if you're working with Go and you use the base file, then to get the full reasoning, you also need to provide Kebi, because the piece of Kebi they're referencing is not included in that file. So they're meant for combining. And Ubergraph itself has some integration tests where it checks out several of the most tightly coupled ontologies from source and builds them every day before they make releases. So it's easier to point out, you guys need to fix this before the next release because there's some incompatibility that's come up. And so that's working really well. There are unintended logical inferences sometimes. So we've been talking about this issue. OWL is not modular among some of the OBO tools team. You'll have, if you go back to the example between Go and Kebi with the metabolic processes, if Kebi makes a change to the chemical hierarchy, and then you reason over Go with this new Kebi, you get a change in the Go hierarchy, which is intended. That's how OWL is supposed to work. But these things can happen, maybe before the Go editors have tested Go with that new Kebi. So maybe they would have wanted to raise an issue or something. So this is not really solved, and I don't think it's not a huge problem, but it's something that we want to try to make sure that the hierarchy published by a particular ontology can be preserved and not have too many unexpected changes to it when you're working with a big merge set. And so as far as scaling, materializing all these edges does kind of result in a big data set. It's not that huge, in the scheme of things. And so it's about 6 times the size of the input ontologies right now, and we haven't had any problems. But query performance is usually really good, but with SPARQL you can always write too complicated queries and timeouts. And so also keeping an eye on alternative triple stores. We could always move to something else besides BlazeGraph as they become available. So I just want to thank my co-authors again, and also Chris Bison at Renzi and Mac Chaffee, who's helped quite a bit with deployment issues and the hosting, funding from NIH. And we have an Ubergraph channel on the OBO Slack, and also open issues and discussion on GitHub. So thank you.
I think we have maybe 1 or 2 questions.
Shout it out.
You can try shouting.
Okay. So you gave the example of transforming X subclass of R sum C into X RC. What about instead of subclass relations, equivalent class relations? Is that preserved in any way in Ubergraph that I can tell the difference? That's a purely Ubergraph technical question. And then if you're willing, a broader OBO Foundry question is, why aren't we making better use of equivalent class statements? Robot has this suggested workflow of reason, reduce, and relax. And it seems like we solve a lot of our problems by sticking with subclass relations. So if you want to answer either part, not really.
Okay, sure. Well, so for the first part, the subclass of is mainly for the translation into a graph edge. But so if you have an equivalent class axiom in the ontology, that's the same as 2 subclass axioms in one in both directions. And so like if gluconeogenesis is equivalent to biological synthesis and has output glucose, that's the same thing as saying that it's a subclass of has output glucose, and also that biological synthesis and has output glucose is a subclass of gluconeogenesis. So whatever.
I think I misspoke.
Okay.
I would be interested in hearing that. How about also X subclass of R sum C? What about X, either subclass of or equivalent class R only?
Okay, so only is not used at all. So it's not part of AL-EL. And so yeah, the focus is just on the sort of structured graph style of queries, like mostly intersections and some values from, which is kind of the core that most of the large terminologies are built on. But that's the kind of what AL-EL was designed for. But yeah, there's no representation of only in there.
I think we better move on, actually.
All right, real quick, I'm just going to introduce myself since I'm meeting most of you for the first time this week. And thank you, Alex, for the introduction as well. So like I said, I'm one of